Alrighty, welcome back to 353. Did I do something wrong? Where the hell is everyone?
Lab 4?
Yeah.
Might be Lab 4 actually.
Lab 4? That's no fun. All right, so today, I guess unlucky for them, I yammer for a bit and then we have fun parallelization practice. So, we're going to go into our last topic of the course, which is persistence, which we will talk briefly about hardware and disks. So let's start off that. So previous operating system courses talk about hard disk drives, which no one probably uses at all, / no one has probably really seen. So I will talk about SSDs or solid state drives. They're the more modern thing. They use those fancy-dancy transistors rather than magnetic disks. So if you don't know what a hard disk drive is, it is storing data on a magnetic platter using magnets somehow to read information from them instead. And it has to physically spin under a head like a record, which I guess you probably are more likely to see a record than a HDD now. But some pros to SSDs is that they have no moving parts or physical limitations, just like RAM, except that the information persists even if the power goes out. They're higher throughput, good random access, more energy efficient than spinning a hunk of metal, and better space density. So it is a lot smaller space to store the same amount of data. The cons are they are more expensive if you are a data hoarder like myself. I have now run out of storage after storing 30 terabytes. So I'm now out of information. But luckily, I bought 120 terabytes worth of disks, so I should be OK for another like 2 months. So cons are they are more expensive. They are, you can buy 8 terabyte SSDs, but they're like $1,000. They have lower endurance, so any SSDs on your machines, there is actually a limited number of writes. Less of a problem now, they're pretty endurant, but at some point in time, they will just essentially wear out. And they are actually more complicated to write drivers for, which we will touch on briefly. So how an SSD is laid out in hardware is it's kind of divided into these parts. So all the storage lives on a die, and then within a die is split into multiple planes. We don't really care about that. What we start caring about is within a plane, there are multiple blocks, which does not correspond to, an actual block. It's just a bunch of data. Usually a block is just, like one fixed size array, like a page could technically be a block, but in this case, they call them different things. So a block consists of multiple pages, and then a page is kind of close to like we have with virtual memory. It's just probably 4 kilobytes, but in hardware, it could also be 8 kilobytes. So SSDs using typically NAND flash are much faster than hard disk drive. Pages are typically matched up with the virtual memory page size. They don't have to be. And the performance characteristics are something like this. Reading a page is quite fast, like 10 microseconds. Writing a page is a bit slower, like 100 microseconds. And then erasing a block, which sounds a bit weird, like actually deleting information, is 1 millisecond, which is quite a lot slower than the other one. And you might be like, what the heck? Why can't I just erase a page? Why do I have to erase a block? And that's the complication for SSDs to write drivers for. I don't know why this is the case. Probably something to do with physics and transistors and things. I don't know. I'm not a hardware expert, so you can ask someone else that is not me. But all I know is that this is the constraint we have for writing software. So for programming NAND flash, we use pages and blocks. So the rules are quite simply, you can only read complete pages and write to freshly erased pages. So after you write to a page, you can't overwrite that data until it is erased. And you can only erase blocks at a time. So each block typically has 128 or 256 pages. And again, that entire block needs to be erased before you are allowed to write to it. And again, this is why writing in general is slow, because I might need to create a new block. I might have to erase a new block in order to actually do a write operation. So it might be actually a lot slower than just the time it takes to do the write. So if you're the operating system and you're writing drivers for this, you have to take that particularity into account. So SSDs need to garbage collect their blocks. So that would be, you use it after a certain amount of time. Some of the pages on your blocks are probably not used anymore. And then if your SSD is otherwise idle, it can go ahead and be like, oh, okay, well, I should probably move those few pages off of this block and just erase this block so that I can actually use it again when the user tries to write more data. So what it would do, again, is just move any pages that are still being used by the operating system to a new block. There may be overhead because I'm just moving information that I don't really have to. The idea is that the SSD will do this when it is otherwise idle, so you won't really notice any performance issues. And the problem is the disk controller doesn't know what blocks are still alive being used by the operating system. So if you just delete a file, the operating system knows what pages are no longer being used. The hardware itself has no idea. So there has to be some coordination between the operating system and the hardware itself. If there's not, the SSD might think that disk is full when a file could be deleted. So it might be the case that every single page on a block is now just not being used. And if you don't tell the disk drive, you're going to have to issue the erase command yourself instead of it just doing it in the background. So the OS can use something called a trim command to inform the SSDs what blocks are actually unused. And then the SSD can freely erase that block without the moving overhead. You just kind of say, hey, OK, just go ahead and erase this whenever you're free, because I don't want to just explicitly wait for you to actually finish that very slow operation. So most operating systems by default have this enabled for you. It's probably called trim as a generic name, or the discard option in the Linux kernel. But it should be there. If it's not there, your SSD is not going to be used to its full potential. It might be slow because it has to actually explicitly erase blocks when it's actually trying to do an operation. All right, so that is a little bit about the hardware. This is the more fun thing. So far we've been talking about single devices. So jokingly, sometimes they are called a single large expensive disk. So it's just one large disk for data and a single point for failure. So if you have all your work on your hard drive and your hard drive dies, which they are known to do, what do? Cry, I guess. So some people do not like the option of crying. So in data centers, or some people will do something called RAID, or redundant array of independent disks. So this is the idea of buying multiple disks, distributing the data across multiple physical disks. And we can use it one of two ways. So we can use redundancy, which is just having multiple copies of something to prevent data loss. So if I have 2 copies of the data, then one dies, it's fine, I don't have to cry. That is one case, and then the other case is that I can actually use redundancy to increase throughput. So kind of like the idea of threads, I can spread up my work across multiple devices to go faster. So the 2 extremes are called RAID. So all the RAID configurations are just called RAID and then a number, and it's up to you to figure out what it is. RAID 0 is commonly called a stripe volume, and the whole idea behind this is to just go fast. So if we just take our file called A and split it up into 8 different parts, so the size of these parts doesn't really matter. It'll be typically like 128K, but it doesn't really matter. So let's say we take a big file called A, split up into 8 parts, and then we can put the odd parts on one disk. So each of these are different pieces of hardware. So this is one physical disk, an SSD, and another physical disk, an SSD or an HDD. So you put half the information on one, half the information on the other. So why would we do this? Well, we would do this purely for performance. So let's say we can, instead of reading the entire file A and all 8 parts of it from a single disk, we can read 4 parts from one disk and 4 parts from another disk. So it would, in this case, speed it up by 2 times, right? Same for writing. Instead of writing all of the 8 chunks of the file to a single disk, I can instead write 4 to one, 4 to the other, and if I do it in parallel, it is 2 times faster than it was before. If I had 3 disks, I could divide it into thirds, and then I would go 3 times faster than before. 4 times, I could go 4 times faster for both reads and writes. All right, what is the problem with this? So let's say I split my file up, so half is on one drive, half is on the other. How many points of failure do I have now in order to lose my data? 2, right? Because if I lose one of these 2 disks, I've now lost half of my file. Half of my file is not terribly useful. I can't actually do anything with it. So the whole idea of this is purely performance, but I'm actually adding more points of failure. So typically, people will do this if they just want something to run as fast as possible. So in like high-end, machine learning or gaming computers, people will do this and do RAID 0 with their disks. And then if a drive dies, whatever, at least I went fast. I will just go ahead and reinstall everything from scratch. You wouldn't put anything important on this. This would just be for performance. So questions about RAID 0. All right, other extreme. Oh, and here's everything I said. So performance only, data striped across all disk and array. Again, you can have more than 2. Fast parallel access, end time speed in both reads and writes, but the con is any disk failure results in data loss. We are actually introducing more points of failure. The other extreme is called a mirror. So RAID 1 mirrors data across all disks. So all disks are exact clones of each other. So if file A now had 4 parts, all 4 parts would be on both disks. So now, if I lose a single disk, have I lost any data? No, right? What about my read performance? Is it better than a single disk, the same, or worse? Same as a single disk? Everyone agree with that? Why would it be the same as a single disk? Yeah? Yeah, so in this case, you could actually still do the reads in parallel. So I could, just because the data is there doesn't mean I have to read all of it from the disk. So I can have the same idea before for reads. I could read the odd half of the file from this disk and the even half from this disk. And if I do that in parallel, then my read speed would go up by a factor of 2, or however many disks I have here. Write performance, on the other hand, is going to be the same as a single disk. So assuming I can do things in parallel, if I have to update this file and add, A5 or something like that, I make the file bigger, I have to write A5 to every single disk. Assuming I can do that in parallel, my write performance is going to be the same as a single disk. But we can do this for as many drives as we want. So if I have 4 drives that are all exact copies of each other, how many drives can I lose and still not lose data? 3, right? So as long as I have 1 drive still alive, I have still my data. I am still fine. I do not cry. So it's simple but wasteful because every disk in the array has a mirrored copy of all the data. The pro is it has good reliability as long as 1 disk remains. You did not lose any data. The read performance is good because it can parallelize it. But the con is it's a very high cost for redundancy. We can do better. So if I have 4 disks, then let's say I have 4 20 terabyte disks. the amount of space I can actually use for my file is just the size of a single disk, right? They all have to be copies of each other, so I could only use 20 terabytes for my file. And the write performance is the same as a single disk, which isn't the greatest. So RAID 0 and RAID 1 are kind of the two extremes. So generally, when you do this, you want to aim somewhere more in the middle. So there is RAID 4. You might ask, what the hell happened to RAID 2 and RAID 3? And they were bad ideas. So we just don't use them anymore and we skip over them. In fact, RAID 4 is a bad idea too. We'll improve it a little bit, but this is just to illustrate. So to illustrate, what we are going to do is we are going to use one disk to store information such that we can go ahead and recover information if any disk dies. So in this case, we have 4 disks, and for RAID 4, across 3 of them, we do striping like in RAID 0. So it would go 3 times faster in this case for both reads and writes. And then we are using disk 3 as something called a parity, which is just some extra information we can use to recompute if any of those gets lost. So one common way to compute parity is just by using an XOR operation. So if we use an XOR, we can use that for parity, is typically what we do. So let's say we have a 1, a 2, a 3, and a parity. So for this, I'll just consider single bits at a time, but for bytes, you just do it for as many bits as you have. Let's say for my information on my disk, I have the value 0 in A1, 1 in A2, and 0 in A3. So what I can do for a parity is I can XOR all 3 of them. So can anyone explain to me, hopefully in more plain English, what does it mean when you XOR more than 2 things together? Yeah?
Counting the number of, or like if there's an odd number of 1.
Yeah, so it's basically, if you XOR multiple things together, it will tell you whether that result of adding them all together is even or odd. So if it's 0, it means adding them all together was even. If it's 1, it means adding them all together was odd, is like the quick way to think about that. So if we XOR all of these 3 things together, our result should be 1, right? So our result is 1, indicating that it is an odd number. So now, knowing this bit of information, if I lose any of these disks, I can actually reason about what I lost. So let's say I lose disk 2. So if I lose disk 2, oh no, have I lost information? Well, no, I can actually get it back. So what I could do, go to the store, get another disk, replace it, and have it recompute that information. So I replace it with a disk, and now I have to figure out what the value is I just lost. So knowing this parity, I can actually figure it out. So it's 0 plus 0 plus something I lost is equal to an odd. That's what this is telling me. So since I'm considering only bits, it's either a 0 or a 1. So it can't be a 0, because if it was a 0, then if I add 0 plus 0 plus 0, that's even. So that doesn't mesh with my parity bit. So the information I lost had to be a 1. So I can always recover it, and I can recover any 1 disk. Everyone get that? All right, what if, all right, let's say we have the same parity, but we lost 2 disks. What can I do now? Cry? So yeah, in this case, I'm pretty much screwed because there's 2 solutions for this, right? So if I don't know 2 things, so I know some unknown plus a different unknown plus a 0 is odd. Well, there's actually 2 solutions for that. This or this. And having a 50-50 dice roll is not great, so I might lose information. But this yeah, this is like 50-50. If you do lose 2 disks in this configuration, you can pay someone a lot of money to recover your data, because essentially, with the coin flip, there's certain ways files have to be structured. So you can essentially try all the different combinations until you get an uncorrupted file, and that's probably what you lost. But you're going to have to pay someone thousands and thousands and thousands of dollars to do that, and it'll probably take them weeks to do that. But there are some tricks you can do to actually recover from this. But it's not guaranteed. So any questions about that? All right, what about, I don't know, read and write performance? Well, read and write performance, like we argued, this is basically RAID 0 across this. So our performance is going to be basically however many disks we have minus 1 for both reads and writes. But there's going to be some overhead here because we're going to, if we update the information on any disk, we're going to have to recompute this information and write it to the disk. So in RAID 4, we can use that parity drive to recover information. So we can use basically all of our space minus 1 disk. So if we had 4 disks that were each 20 terabytes, and we use this to store our files, we could actually use 60 terabytes of space. And in this case, we require at least 3 drives to be able to do this. So the pro is that you get n minus 1 times performance. Basically, it's just RAID 0 minus the parity disk. And then the nice thing about this is if I lose a single disk, I can just replace the filled disk and rebuild it. The con is that performance can suffer because every write, no matter to which drive, causes a write to the parity disk. Yeah? In this, it would be both read and write performance. Yeah, so this is like the n minus 1 times read and write performance would be, in general, just because this part acts as a RAID 0, right? But it's going to be slightly worse because we'll also have to write to this no matter what. So for instance, let's say I'm writing A1, B2, and C3. So if I write that, I could do those writes in parallel, but I'll be a bit stuck because that will cause an update to A, B. I'll have to recompute the parity for A, B, and C. So it'll kind of cause more writes on this drive. So there'll be slightly less performance than just straight up n minus 1 RAID 0 because of the parity disk. All right. So questions about that before we get into the next RAID? So next RAID is the one that's actually going to be used. So RAID 5 is the exact same idea as RAID 4, except this parity information, instead of being concentrated on a single disk, is distributed across all of the disks. So same idea. We basically have 1 disk worth of parity, but instead of everything being concentrated on the same physical disk, we kind of spread it out over all the disks. And the whole idea is that you spread out all of those writes, and then hopefully you get better performance. But the same idea is the same. All right. So funny story. I had my thesis stored on a RAID 5 array. I was working on it. 1 drive died. Did I lose data? No. Was I a poor student and was I close to the deadline? Yes. Did I replace that failed drive? No. Typically, hard drives die typically, close to each other. So a few days go around. Another drive dies. Do I lose data? Yeah, I did. Did I cry? A little bit. It died, but I actually recovered most of it, and I had stuff. I only lost a few files, so it wasn't that bad. But moral of the story is if a drive dies, you should probably go out and replace it, and especially if you're teetering on the edge. So RAID 5 is basically just an improved RAID 4, all the same pros as RAID 4, but the write performance is improved because we're no longer bottlenecked on a single parity drive. All the information is distributed instead of concentrated. All right, so next fun RAID level is RAID 6, which just adds another parity block per stripe. So before, we had one disk worth of parity called P. I distributed across all disks. Now I have another block or another bit of parity information called Q, which I also distribute among all the disks. So you might be thinking, oh, how do I compute Q that is different than P, which is just an XOR? And to explain that, that is beyond my reasoning because it has to do with math, Galois fields, and a whole bunch of things. It's like a linear combination of XORs or something like that. I don't know. You can figure it out if you like math. I don't. All I know is that it kind of works. So in this scenario, kind of like RAID 5, except now I have 2 bits of parity, so I can lose up to 2 disks at a time without losing data. Yep?
How does distributing the parity bits decrease like the overhead? Because aren't you writing to the same number of like parity bits?
So you're still writing to the same number of parity bits, but you're distributing it instead of concentrating it on a single drive. So like for this one, before, if I updated A1, B2, and C3, all those writes were concentrated on the same drive, right? But now, updating to A just causes a write here, updating B causes a write here, and updating to C causes a write here. So I'm more likely, instead of doing 1, 1, 1, 3, it's more likely 2, 2, 2, 2.
1, 1, 1, 3 is?
Yeah, 1, 1, 1, 3 is bad because you'd have to wait for that operation to complete. You have to wait for 3 writes to happen all on a single disk, right?
Oh,
Yeah, so it's going to be as slow as the slowest one, so we don't want to concentrate them. It'd be better to have 2, 2, 2, 2, or get some 2s in there. All right, so yeah. Going back to RAID 6, I should have probably had my thesis on this because if I lose 2 drives here, I can actually recover, right? But if I lose 3, then I'm probably screwed. So RAID 6 can recover from 2 simultaneous drive failures because it has an extra disk of parity. So because of that, I have worse space utilization. So I'm essentially now using 2 disks worth of parity information. So if I have only 4 disks in this case, and they're 20 terabytes each, I can only use 40 terabytes to store my data because of those 2 parity drives. And to do this, I need at least 4 hard drives. The write performance is going to be slightly less than RAID 5 due to another parity calculation and more writes happening just due to more parity information. So there's some other fun RAID arrays. I will save you the hassle. If you read the textbook, for some reason, they redefined what the hell RAID 1 is. So if you read the textbook, they say whenever we say RAID 1, we mean RAID 10 or RAID 1 plus 0. So what those are something called nested RAID levels. So just RAID 0, 1, 5, and 6 are not the only other options. I can combine RAID levels if I want. So a typical one is called RAID 10 or RAID 1 plus 0. And it's called a nested RAID level, so you can idea it's, in this case, like a stripe of a whole bunch of parity disks. So there's 2 ways to nest them. I can either, let's assume we have 6 drives. If I have 6 drives, RAID 10, which is RAID 1 plus 0, typically how you read this is the number at the end is what the highest level is. So I would have a RAID 0 array at the top. So I'm striping a whole bunch of pairs of disks. So every pair of disks would be a RAID 1 array. So I could do something like this. So I have a RAID 1, and our RAID 1, we have a mirror of 2 disks. So then I would just have 3 pairs of 2 disks. So this is disk 1, disk 2, disk 3, disk 4, disk 5, and disk 6. So now, if I did something like this, how many drives could I lose before I lose data? And to put numbers on them, so whoops, if I have a bit of information, let's say I have, A1, well, these two are mirrors of each other, so they would both have A1 on them. And then my outer level is striped at the top, so that big A file would be split over a whole bunch of different pairs of RAID 1s. So this would be like A2, A2, and this would be A3 and A3. So how many disks can I lose without losing data? Yeah? One or more.
Like if you happen to lose disks spread out,
Yeah, so there's kind of like a max and a min, right? So the worst case is something like this. So let's say no matter what, I should be able to survive a single disk failure, right? So let's just say I knock out this one. So if I knock out this one, I have not lost any data. I still have a copy of A3 somewhere, right? If I get unlucky and I take out this one, I have lost data, right? So I'm guaranteed I can survive one disk failure, but I'm not guaranteed I can survive two, right? So if I take out the partner, I'm now screwed. Okay, well, that's the worst case. What's the best case? Well, if I just take out another one of a different pair, right? So I could take out this one, and I don't lose data anymore. I still have a copy of A3. And I could take out this one, don't lose data anymore. I can take out a copy of A1. So I can, in the best case, I can lose 3 disks without losing data, but that's not guaranteed. Worst case, I can only lose a single disk without losing data if I'm unlucky. But if you want to play the lottery, you can do something like this. If I have more pairs, I'm more likely that I won't take out a partner, so it gets better and better and better. And also, sometimes, typically, you would prefer this over RAID 5 or 6, typically, because also when you're recovering data for practical reasons, that causes a lot of reads and writes to happen to the disk that you are recovering from. Also, it takes a long time because it has to read all the parity information or read the content from the data to either recompute the parity or use the parity to recompute the data was lost, which stresses out the drives, which makes them more likely to fail as well. In this case, in order to just do a replacement, so let's say, rewind a bit and say disk 5 dies. So if disk 5 dies, well, it's easy to replace it. I just get rid of the disk. I replace it with a shiny new, disk 5. And then to recover, I don't have to recompute the parity information at all. I just have to make a copy of disk 6. So it just has to copy information from disk 6 over, not involve any of the other drives. So we can just recover. We don't have to recompute anything. It's just a straight copy, which is usually a lot faster than having to read every single drive in my array. So you might prefer something like this. In terms of space utilization, let's say each of these drives, again, was like 20 terabytes. If each of these drives were 20 terabytes, how much storage can I use for my actual files? Anyone? Yeah, 60, right? So because these are copies of that, in total I have 120 terabytes. But in this case, these two are mirrors of each other, right? So I have the same data on both, so I can only use half of the data to actually store something useful. So I would only have 60 terabytes usable. And in general, it would only be 50% of my space. And as you might imagine, there is also something called, you do not need to know this difference. I don't really care about this difference, but you might also see something called RAID 01. Same idea, just flips it on its head. So we have a RAID 1 array at the top, and then at the bottom we have a mirrored copy of two RAID 0 arrays. And then these RAID 0 arrays would each have, in this case, if we have 6 disks, would have 3 disks in them, so it would look something like this. So we won't get into like the very subtle differences between these two. Just know that there's 2 different ways to do it. But typically, you would always prefer this one for reasons we shall not get into. But I can combine different RAID levels if I want. You could have, you know, a RAID 50. You could have a RAID 60. So a RAID 50. Whoops. Wow, I can't type. So RAID 50 would be the same as 5 plus 0. So same idea here, but instead of RAID 0s here, I would have RAID 5s, which I would need a hell of a lot of disks to do. But again, it's something you can do. If you are Google or something like that, that has to deal with vast quantities of data. Again, for this, we don't really care about nested RAID levels all that much. Yeah?
So is A1, A2, A3 just like segments of a single file?
Yeah, so A1, A2, A3 would just be 3 pieces, all mutually exclusive of the same file. All right, any other questions with that fun stuff? So probably care about that if you're running a server, things like that, so you don't actually lose data, or if you actually care about. So you might have your data backed up on the cloud. So the cloud, just another word for someone else's computer, and you're just paying someone else to do this for you. So they'll be using something like this to actually store your data so they don't actually lose it. Because hard drives die all the time. If you're thinking about job prospects, someone's job at like Google and Amazon data centers is to just go around on a scooter with a cart of hard drives and just keep replacing hard drives as they die. So they die quite often, so that's a full-time job if you're interested in that fun stuff. So disks are the important thing. They enable persistence, so storing data and actually retrieving data as well. So we explored 2 topics in the first half of this lecture, SSDs and RAID. SSDs are more like RAM, except, well, 1, we don't lose data when the power goes off, and we have to access them in pages and blocks instead of just pages like we have with RAM, how we use virtual memory. And then SSDs need to work with the operating system for best performance, so we need something like trim in order to tell the SSD that, hey, these are the pages on the block we are no longer using. If we want to tolerate failures of disks because they do die all the time, having your important information just on a single hard drive is a very, very bad idea. So you can use something like RAID to tolerate failures and improve performance using multiple disks at a time. So with that, we shall take our break and then come back for our fun performance example, which will help a ton for Lab 5. Alrighty, so let's do the fun thing. So this will help you for Lab 5, and it's more of a realistic way of like, hey, let's use threads to make our program better, and let's screw it up lots of times. So, like I alluded to in the last lecture, it's banking time. So, we're running a bank. We're going to simulate doing 10 million transfers. So we have a simulation that creates a varying number of accounts. The rules are quite simple. Each account has a unique ID and a balance. We'll just assume everyone starts with $1,000. And we are going to generate random transfers between random accounts for 10% of their current balance. So it's a zero-sum game. If we're the bank, we're just facilitating doing the transfers between accounts. So we're just sitting there doing money or transferring money. Nothing bad should happen, right? So we're going to assume in our code, we have to call the securely connect to bank function before doing the transfer. We'll assume that it is very slow, and that's something we want to do in parallel. So we are going to use threads to make things a lot faster. So the rest is done live. We'll have, if we're lucky, well, we will, because I'll ask you to program this. So of course, we'll have lots of errors. So we're going to have data races. We're going to have deadlocks. We're going to laugh. We're going to cry. We're going to have a good time. So our goal is to be faster than 11 seconds. So you can find this in the examples repository or the examples directory as well. In the lectures, it's here. It's this lecture, setup, build, and it's just a bank sim that takes a single argument, the number of accounts. So let's just run our code. So just to see how it works, and we'll start going over the code. OK, I need to compile it. So if I compile it, I get some errors or some warnings I'm going to ignore. And then let's just assume that I am simulating creating 10 transfers. So 10 accounts, if they're $1,000 each, my bank should have $10,000 in it. Takes some time to simulate the transfers. At the end of doing all of the 10 million transfers, as a sanity check, I'm a bank, I want to count my money. The money I have across all the accounts before should be the same as after doing all the transfers, right? I don't want to lose, make up money, or otherwise do anything that might get me put in jail. So if I run this and I use user bin time, we should see that on the system, it should, take about 11 seconds. Let's see. So whole bunch of information, So total time took about 10 seconds-ish. 10.8, pretty much 11. So let's look through the code. So I have a few defines at the top just to make sure things are usable. So we have a starting balance of 1,000. We're going to have num transfers as 10 million. And then I know how many threads will parallelize well on this machine, so it's 8, so I'll define num threads. Currently, the solution does not use threads at all, so our job is going to be able to create 8 threads that all operate in parallel. Now I have the struct called account, and this is all the information I need for a single account. So right now, I just keep track of its current ID, and then its current balance. So I'm going to, since I don't know how many accounts I need at runtime, I'm going to allocate them when I run main. So I'm going to need all my accounts accessible in my thread function. So I'll just lazily create a global variable called accounts, which is a pointer to a struct array. This will be an array that I'm going to allocate once I know how many accounts to create. And then I'll initialize the number of accounts and the pointer to the accounts array as 0 and null. Then I have the securely connect to bank. Doesn't matter, it just wastes a bit of time. Then I have my transfer function. So it takes by pointer an account from an account to. So I need to send the money from the from account to the to account. So I'm going to call securely connect to bank. Right now, simulate's just wasting some time. So I calculate the amount I want to transfer, which is from. I'm just going to use integer division. I don't really care. So I'm still going to get the, it's not going to be exact. I'm not going to keep track of cents. But all of the math should work just fine, and integer division's a lot easier to reason about. So I'll just do integer division with 10, and then take that amount, subtract it from the from's balance, add it to the to's balance, so I'm transferring money between accounts. From the bank's point of view, I'm not losing anything, doesn't matter to me, right? So this is a run function, so we're going to use it with pthread create, so it takes as arguments, I have it setting up that it passes a thread ID, it mallocs, it does all that fun stuff, so we can get a unique thread ID for each thread, which we will go ahead and use at some point, and then I can free it. So that has nothing, we are going to fill that in. I have check error, which just does the normal thing of check for an error, kill the process if there is an error. Then in main, I'm going to make sure there's exactly 2 arguments, so the program name, number of accounts. The set local is just so I can see it adds commas for me. And then I'll get the number of accounts to simulate. So this is actually how you have to use this account to actually error check. So you set error node to 0, call it, and then if that number is 0, it will set error no. So this is just how I check for errors for it. Don't worry, these asserts won't happen as long as we write a valid number. Then I allocate the account, so it's number of accounts times the size of a struct account. Malloc that memory, so it's enough for a big array. Make sure that it actually worked. It's not null. Then I just print how many megabytes we used, just in case VS Code crashes or something like that, and I don't push up against the memory on my virtual machine. Then here, this is just initializing the balance of the account, so everyone has a unique number. Starts at 1, goes up to however many accounts we have. Everyone gets $1,000. So my initial funds should be just starting balance times the number of accounts I have, right? That's how much money I have. So this is just so I can copy and paste it once we create threads. So I'll skip over that now. So this is the main part of the code that we're going to try and parallelize. So this is doing the transfers between 2 accounts. So this just loops over I as many transfers as we're going to do. We'll see that we're not using the value of I. We don't really care. It's just keeping track that we're actually doing 10 million transfers. So it generates a random from index. So it just does rand mod number of accounts, to index rand mod number of accounts, and then just does a transfer between them. So it does the array subscript from index to index, does normal C things, gets the address of so that it's a pointer to an actual account, and then calls that transfer function we saw before, which actually subtracts and adds money to the accounts. So this is the only loop we want to parallelize. Then here is just the sanity check. So this is the total balance. We're going to calculate what the total balance is across all the accounts whenever we're done doing all the transfers, and it should add up to be the same as what we started with. So this just loops through all the accounts, adds their balances all together, and then make sure that the bank's final funds, just print out what the final funds are, which should match, and then freeze, we free, get rid of our allocated memory. So we're going to start by parallelizing. We're going to make things go fast. So here is the boilerplate code that I already wrote for you. So we want to parallelize that stuff. So we're going to make threads. So we're going to make an array called threads up to num threads. So there's going to be 8 of them. And then we're going to malloc space for a thread ID, which is just an int, write the value to that, and then pass it to the thread function just so that each thread gets its own unique thread ID. And then we do what we did before, pthread create, the current thread in the array, default attributes, so they're joinable threads. Start routine is just run the run function, and then give it that pointer to that thread ID there, and then hopefully that works. So after this loop, we create 8 threads that are all running that run function, hopefully in parallel if my operating system is good and actually using all my hardware. So after I create all 8 threads, the main thread just joins them all. So I won't be able to pass through this loop until all of my threads are done. So after all my threads are done, I'm done all of my 10 million transfers, so I can go ahead in the main thread, do the sanity check, make sure my money is still there. So what we are going to do is, I'm going to need help. So we are going to parallelize this loop. So let's start it. So this is my run function. Should I just copy and paste this into my run function? Well, is this it? I've now sped up my program by 8 times? No. What is my first thing I need to do to make this fast? Yeah, if I have 8 threads, each should do 1/8 of the transfers, right? So right now, each thread is doing num transfers. So each thread would be doing 100 million, which I don't want. I want to do 100 million in total. That would be 80 million, which is bad. So I'm trying to divide up the work among all the threads, so I can just do num transfers divided by num threads. So each thread would get 1/8 of the work in this case. The number cleanly divides. I won't worry about any leftover, whatever, it doesn't really matter. So I'll just do something like this. All right, so are we good now? I'm now the greatest 10x programmer in the world, well, 8x programmer. I've now made my program 8 times faster. No bugs, no problems at all, right? Yeah. Won't the threads interfere with each other with what? The mod?
The mod might take like more than one operation. It's just like the example of where they all like add to the global variable. Does something similar happen?
Oh, so anyone help with the term? What is a bad thing that might happen with threads that causes weird issues? Anyone remember the term? Yeah. Yeah, a race condition or a data race. What's the definition of a data race? Anyone? Yeah?
Multiple threads use the same write command, or like write operation, or write to the same. There's like multiple write.
Yeah, very close. Anyone help her? Yeah.
Multiple threads try to use the same data, but one modified before it got read, or before/after it got read by another thread.
Very warm. Yeah.
Writing to stale data.
Writing to still data. Yeah, you could define it as that. Technically, 2 or more concurrent accesses to the same memory location with at least one being a write. So for this mod one, this num accounts is shared between all threads, right? Are we writing to it? In this mod? No, we are not writing to it, right? So there's no data race. At no point are any threads, so each thread runs this run function, which reads num accounts here, then calls transfer, and then transfer. I assume this is thread safe, no data races or anything like that. And then here, it doesn't use num accounts at all, right? So num accounts is only read between all the threads. It's shared, but it's only read. So we don't have a data race with num accounts. So I like what you're thinking about, something with the mod. What about rand? So rand's called with multiple threads, right? So did we write rand? No. So we're going to have to check if that's thread safe, right? So we can go ahead. If it's not thread safe, bad things are going to happen. Although you could argue if rand's not thread safe, you just get a random number, and that's really good. So it's even more random. But we can check. So in the man pages for rand, I can search for attributes. Is this the right page? Man 3 rand. Rand 3. Yeah, this is rand. There we go. All right. So I don't know what the hell I pulled up before. So if you look at the documentation for RAND, it says RAND, RAND underscore R, and SRAND, thread safety, thread safe. So that's good, right? It's safe. So yeah, we're getting confident now that our code is great, right? So this should go 8 times faster, right? All right, well, let's assume. Let's see if we get fired today. So let's compile it and run it. And we can time it too, just to make sure that it goes fast. I'll make it, if I do -p, time will give me something a bit nicer. So I'll do it with 10 accounts. So managing $10,000, 1 Mississippi, 2 Mississippi, 3, oh, there we go. So it took 11 seconds, which wasn't any faster, and I just made $94,000. So we're fired. So help. Okay, number 1. Took 11 seconds before. It took like 10 seconds before. I have 8 threads, each doing 1/8 of the work. I'm not synchronizing. I'm not making anything serial. So why the hell isn't this 8 times faster? Any guesses? This one you probably won't be able to get, but you could make an educated guess. Yeah?
If it does 8 threads, but it still has to run that many operations in total. So
Yeah, but it's spread out over 8 threads, so it should be 8 times faster, right? We're doing it in parallel.
the processor really just runs one at a time.
Nope, my processor has I have more than 8 cores on this. Yeah?
It's not necessarily true that each thread just does one thread at a time.
It's not necessarily true that each thread just does one. Each core does one thread at a time.
If you like multiple threads are stacked on one core.
So if my operating system was complete garbage, that might happen. I have a good operating system, though, so it will run things in parallel. All right, so this one is a bit more subtle. So this RAND function, we saw that with thread safe. Does that mean it is fast? No, you could imagine that RAND probably modifies some global state, right? So if it's modifying some global state, it would probably need to use a mutex and lock it, which would make it serial. So if I do this, all my threads are calling RAND, and in this case, RAND seems to take most of the time. So they're all blocked waiting for RAND to be thread safe, so they're all just wasting their time waiting for RAND. So if I read the documentation, first step, again, that you outside the scope of this course, more of a performance thing, but they're all using some global state in RAND, which is really, really slow. So instead, I can create a local variable in each thread called seed. I can initialize it to the thread ID. And then there's a version of RAND that's called RAND underscore R, where I can give it the state. So I can give it the pointer to the seed, and then it will use that to actually go ahead, modify its own state, and then each thread will be modifying its own state so that it can all be done in parallel. So if I do that all in parallel, compile that, so this will make RAND actually independent in each thread because they're all modifying their own state. So each RAND R should be a lot faster. So if I do this now, and I run it, boom, it is now 8 times faster, right? It makes more sense now. Holy shit, Jesus. All right, so we have more money than the planet, so if we are called on to actually, provide that money, we are 100% going to jail. But it's fast at least now, right? So took about 10 seconds before, 8 threads. Now it takes about the 1/8 of the time. Makes sense, right? So my operating system is not complete garbage. It will run in parallel. All the threads are fighting over that one, or all the global state in that RAND function because it's marked as thread safe, yada, yada, yada. All right, so that result, obviously bad. Fix, please, what happened? Yeah.
If that happens, because we're modifying the accounts variable, that's shared between the
So yeah, let's make it. So what are we modifying, which may have a data race?
accounts.
Accounts, what specifically about the accounts?
Balance.
Yeah, balance. So is it possible that we have a data race for an account's balance? So is it possible that we have two concurrent accesses? So two concurrent accesses between threads such that there is the possibility of a data race. Well, yes, indeed there is. Could happen that one thread is transferring from thread A to thread B, and another thread is transferring from thread B to thread A, or thread A to B. In this case, it doesn't matter. In which case, they'd be both modifying A's balance and B's balance, so there could be a data race between any of those balances, right? So that's bad. Well, let's see. So this is also a case of why, programming with threads is hard. So let's say we were, a large, successful bank that you are gainfully employed at, and you don't only have 10 accounts. You implement this as is, and you have like 1 million accounts. So if we run that, we are managing $1 billion, and that's pretty decent, right? We only made up 164. Let's say we were running a bigger bank. So we're managing $10 billion. No bugs. Right, we're all good. So this is the weird case where the larger your program, or the larger your problem is, the less likely you are going to encounter an error. Anyone want to explain why it was worse with more accounts and, why it was better with more accounts and worse with few? Yeah?
I guess it's less likely for two accounts to have a database if there's a lot of accounts, like for random accounts, it's very unlikely for them to access the same account.
Yeah, I'm randomly transferring between accounts. So if my problem was a data race here, right? Two concurrent accesses to the same account. So one thread was trying to do something with account A, and another thread was also trying to do something with account A. Well, if I have whatever that number is, like 1 million accounts, the likelihood of picking the same account that two threads are actually using at the same time is fairly low. So I might not actually see the error. While if I only have 10 accounts, the likelihood of 8 threads each picking the same account is quite high. So if, again, run it, boom, I am now richer than anyone on the planet. Or if I'm caught, or if I have to service that debt, then I am completely screwed. Yeah?
Is that big number caused just by a lot of, is it caused by overflow?
Yeah, so that would be caused by overflow. So as soon as I overflow one, boom, the number just gets super screwed. I might get super unlucky where I don't overflow and it just some giant number. Let's see, 100. Yeah, still have a lot of money. Sometimes we can, better. No, we're still screwed. All right, how to fix. How do we prevent a data race? Yeah. Use a mutex or a semaphore. So typically with data races, two concurrent accesses, we want to use a mutex. Mutex is the right tool for the job. All right, so I need to use a mutex. Tell me what I should do with this mutex. Yeah?
Is it possible to make a mutex for each account and lock each account instead of these accesses?
Yeah, so the idea there is, well, should I create a mutex for each account? Probably a good idea. Well, because this is where I have my data race with the balance, right? So we all agree we have a data race with balance. So one solution I could do that would be safe is I can go ahead, I can just create a mutex, and then I can just do a lock. Actually, we can just do that. So let's say I create a mutex. equal to p. And then I do something like pthread mutex lock. I can just lock all of the problem code, right? So I'll lock the mutex. Whoops, what did I close? Probably doesn't matter. So I can lock the mutex and then unlock. So I make this a critical section, so only one thread can do this at a time. Will this have a data race? Will I have more money than anyone on the planet? Oh, it shouldn't have a data race in this case, right? So I'm essentially using one lock, locking just the problematic code. I could, of course, also do this and add the securely connect to bank into the critical section, but that will make sure that no threads can do this in parallel with one another. And I said it is safe to do in parallel, so we should move it out, let other threads do it in parallel. So this will just prevent these 3 lines of code from running in parallel or concurrently with any other thread. So if I compile that and run it now, 1 Mississippi, 2 Mississippi, 3 Mississippi. Oh, it took a lot longer in total. It took 12 seconds. Didn't lose any money. But yeah, a bit slower, not 8 times as fast. So we want to do better than this. So as we discussed before, one thing is like finer grained locking. So I could create a mutex for every account, right? So let's do that. So let's go up. Thankfully enough, in this struct account, I can just add a mutex here, right? So just add a mutex for every thread. So with that, I'm going to have to initialize it too. So I'm going to have to come down to where I initialize it, and I'll just initialize every single account's mutex. So that would be accounts i.mutex. So we have to do pthread mutex init, init, and then address of that. Too few args. So that, and then null default attributes, we don't care. So that creates our mutex for every single account. Great. Now what? So I don't need to use the mutex for this part, right? We already fixed this part, no data race with this part of the code. The problem was in transfer, right? So this is all good, no data races. We're concentrating on this. So now we have a mutex for each individual account. So what code should I add to make this now thread safe? Yeah. So yeah, I want to pthread mutex lock. So first one you said I should lock the mutex from the from account. So from's mutex, and then the to account, right? Is that all I need? Yeah, unlock after, right? So unlock where? After the to bounds. So here, and we can go ahead and just do, unlock. All right, so is that good? Yeah.
Just a small question here. Should we also add like sort of a guard lock?
A guard for what?
Like because after we lock from some other, I'm not sure, like there could be some data race in between the 2 locks.
Some data race between the 2 locks?
I'm just guessing.
So what's our primary concern if we have more than 2 locks? Yeah.
Somehow one lock can prevent the other lock from being unlocked.
Yeah, what's the name of that? Uh-oh. Deadlock, right? So deadlock is you have a lock, you're trying to acquire a different one, and you are not able to. So ways to prevent it are I either acquire locks all the time in the same order, or I get rid of hold and wait, right? So in this case, looks like I'm acquiring them in the same order, right? All the threads are doing from and then to. All right. So does this look good to everyone? This is a perfectly cromulent example with no bugs. Perfect. All right, so let's compile it. Do we want to assume we are a big bank or a small bank? Yeah. Which one? Small? All right, let's assume we're a small bank. So let's just 10 accounts. All right, so time to beat. So let's see, scroll up. So real time is like real clock time. User time is time across all cores. So we're doing about 12 seconds of work. In that case, we didn't exactly do it 8 times faster because we were blocked. We just had a single mutex before. So that's why we got that. So real is the time we actually care about. It's like how many real seconds pass. So we just added these locks around here, and we argued that it's all good. So time to beat, 5 seconds. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi, 9 Mississippi, 10 Mississippi, 11 Mississippi. We're worse than not using threads, and we are definitely fired. So, anyone want to explain what happened? What is going on? So, one thing I can look at is if I go open a different shell and type htop, I can see what my threads are doing. I have 10 threads on this. I can see that, they're not really doing anything. So that's kind of telling me something. Does that give me evidence that I have deadlocked myself? Yeah.
I think the issue is that you said that we should always lock from and to, like in the same order, but then the from account might be a to account in another thread.
Ah, yes. Perfect. So we are accidentally deadlocking. So how we could deadlock, and this is a skill you need for the exams and figuring out what could deadlock, right? So in transfer, we did lock from and then lock to. And we took them by a pointer from and to. Well, there's no reason that thread 1 can't do transfer, let's just say A to B, and then thread 2 couldn't do something like transfer B to A. So in that case, in the implementation, or well, when we run transfer A to B, that would be the same as lock A, lock B. In thread A, the from account is now B, so that would be lock B, lock A. That looks bad. So could be the case where thread 1 runs first, locks account A's mutex, then we context switch over to thread 2. It locks account B's mutex, and now we are at a deadlock, right? So this one can't progress because it's waiting for that one to lock. The other one can't progress because it's waiting for the other one to unlock. So we are now in the deadlock scenario. So this is still running because it's deadlocked, so I have to Control-C, kill it, and then, yeah, so real 100 and, yeah, it definitely is deadlocked. So how fix? Yeah.
Just lock one thread at a time. Oh, it's lock one mutex at a time?
What?
Like we're only actually modifying from one line
Yeah, so there's one suggestion of like only lock one mutex at a time, so we don't have that. That will be thread safe from the point of view of the bank, but the transactions won't be like, the transaction itself won't be atomic, so each account would have a slightly different balance than if it just went serially, which is generally what we don't want. So without that subtle bug, assume that we have to have both mutex locked. Yeah?
Will you just always lock the smallest account ID?
Yeah, so to prevent a deadlock, two different ways to do it, right? We can either we only have to break one condition. We can either break a circular wait, or we can just go ahead and break hold and wait. So the suggestion was, well, in order to break circular wait, we need to order them somehow. Luckily, each account has an ID, which is unique, and we can just always lock the account with the lowest ID first. So that would give us some type of order. So to implement that, I could just do something like this. So I could do pthread mutex tm1. Oh, I could do a pointer to m1. Yeah, let's just create two variables, M1 and M2, and then we can just check their accounts IDs to see who is smallest. So we can check from's ID. So if from's ID is less than 2's ID, then we'll say M1 is equal to from's mutex, and M2 is equal to 2's mutex. And then otherwise, we'll just flip them around. So we'll do something like this. If the 2 ID is, or from ID is greater than 2 ID, we'll make M1 equal to 2 ID because it's smaller, and make M2 equal to from ID because it is larger. So now, in this case, I can go ahead and change this to lock M1, the smallest one first, and then M2, which is the bigger one. Then I should change these two as well. Oops, M2. All right. So is that better? No deadlock, we're keeping our job? Yeah?
I'm not sure about this, but could it be possible if 3 threads try to call and they have like a big circular?
So if 3 threads call, is it possible to have a big circular? Is that it shouldn't be, right? If we always acquire the lowest account ID first, there's no circular wait. It's not a circle, right? We're always doing it in the exact same order. So this shouldn't deadlock, right? All right, well, we're confident. We don't have anyone objecting, at least. So compile it. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi, 9 Mississippi, 10, we're fired. So, any ideas? You still have a bug. This one's a bit harder to reason about. Anyone help? It's 5 minutes before the lab deadline. And I left my debugging to the end. Yeah?
If you had like, I don't know, 2 calls where it's like the same account ID in both the threads, but then in one it's the maximum and one is the minimum. And
The maximum and the minimum.
in one it's the higher account ID and one is the lower account ID. So then you lock.
So you're saying we have 2 threads doing transfer. So which accounts do you want to transfer between?
Maybe like 2 and 6, and then.
Oops, 2 and 2 and 6, or other way around.
I don't know, 'cause
I think you said the answer right at the beginning. You were so close. Yeah, I think you.
It's a valid transfer between two accounts of the same, just two of the same accounts.
Yes, you said at the beginning the same accounts. So what about if I was transferring here between account 2 to 2? Whoops. Well, that's probably bad, right? So if I'm transferring from account 2 to account 2, then their mutexes are the same, right? So I lock it, and then M1 and M2 would be the exact same mutex. So I lock it, and then I try and lock it again, which I deadlock myself. So luckily, in this scenario, we can actually kind of make this a lot easier. So we could just check if the from is equal to 2. So if both the pointers are equal, it means this is a shortcut. They're definitely the same account. So does transferring to and from the same account even do anything? No, right? So I'll just skip it. I'll just return. I don't have to do anything because it won't do anything. So why even bother? All right. Are we good now? So what? We screwed up how many times? Like 5 times, 6 times, 7 times? Will we keep our job now? Let's see. So main problems we have to always think about is possibility for a data race. Well, originally, yes, there's a data race to account balance. It could either be from or to, but now we've protected against the data race because now we make sure that this code can only run from one thread at a time that has a lock for both of the accounts. So we can't have concurrent accesses to balance for more than one thread with at least one being a write. So we're good for data race. And then the other condition is deadlocks. So to prevent deadlocks, we can either eliminate hold and wait, or we could always make sure things are totally ordered and there's no circular dependencies at all. So this time we were like, okay, let's just go ahead and always acquire the lowest account ID first and then the highest next, so they're always in the same order. And then we had that subtle bug where, hey, we don't want the mutex to be the same. So it seems like we have all of our bases covered, right? So let's see moment of truth. Let's compile and run. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4, oh, yay. So did about as good as a single lock before, but we didn't lose any money, which is great. So let's see if it works. If I do, what would we expect if we have way more accounts now? A lot of memory, yeah, true. What about runtime performance? Yeah.
More better runtime because less locking.
So better runtime because it has less locking. So
Less like stalling.
yeah, less, what's the word? Contention, right? Less contention. So we have the same amount of locking, but it's more likely that the threads can run in parallel because they're all accessing different accounts. If they happen to access the same account, then it will go as slow as the serial version. But if they don't overlap, then we can run all in parallel. If we have more accounts, it's likely that we run more in parallel. So yay, look, we didn't lose any money and it went a lot faster. So the more accounts we have, the less contention we have, and the more worthwhile it was to actually write this in threads. So we can go ahead, test it extremely. So if we only have 2 accounts and we have 8 threads, oh, well, that one runs faster. Anyone, because it's very likely that it's going to be the same account, right? So minus that kind of optimization, it falls off after a while. So let's say 20. So if we have 20, we can see that, yeah, it's quite likely that they'll interfere with each other. Actually, that was slightly better than 10, but whatever. the more accounts we have, less contention we have, and the faster it will likely be. So we have created the world's greatest bank of all time, just like I promised. Any questions about this? All right, I will show you a cool little tool then. So let's say, okay, so let's rewind, and let's say we still had the deadlock issue. So I'll just always acquire from mutex and to mutex. So let's say we rewind and still have the deadlock issue. Compile. So debugging this, you might be like, oh, okay, well, maybe it just will take a long time. Probably hard to debug this. So Valgrind won't help me, right? Some of you probably use Valgrind. So it won't help you here. But there's a cool suite of tools called the sanitizer tools. So there is a tool called a thread sanitizer, which will add a whole bunch of runtime checks to your program to check if there is a data race or if there is a deadlock condition. So how you do it is, so on this, we have to make sure we use the Clang compiler. You can use it with GCC, the default compiler, but you have to install some other packages. But how you do it is we use Meson. You can set it up and then add this flag. So this is a /d, that's a defined flag. So there's something called desanitize equals thread. So that will add all of the compiler flags and linking flags it needs to add all of these runtime checks to your program so that when you compile it and run it, it will tell you at runtime if there is some type of threading problem with your program. So if we do that, sets it up, and then it says user-defined options, we're sanitizing the thread. So we can go ahead, compile as normally, should all work. And now if we run our bank sim, so let's run our bank sim with 10 accounts now, it should make things very angry. So we do that, and it gives us a whole bunch of output. I'll just stop it. So this actually tells you what happened. So it says, warning, thread sanitizer, lock order inversion, potential deadlock. Another way of saying lock order inversion is just it is a circular dependency. So it actually tells you what the cycle is. So it's showing here that mutex 0 is trying to, is held and it's trying to acquire M1. M1 is held and it's trying to acquire M0. So it's telling you the cycle. So here it even says M1 acquired here while holding M0, potential deadlock, and then it throws up on you over and over and over again. And if we get lucky, we even get cooler cycles. So there's a cooler cycle here involving 3 threads. So M0, M1 to M3, all the way back to M0. And if we get super, super, super unlucky, oh, this one looks, no, that's not that much fun. And we don't have any fun deadlocks. But we can, it actually will tell us if there's a potential deadlock in our code, so it might be nice to help you debug. Another problem we had that was hard to solve is our data race problem, right? So whenever we deleted this, we didn't have a mutex at all. Let's just keep that optimization. So this is the case where we actually had a data race before, right? Where we just got some giant number at the end. Well, if we run this with thread sanitizer now, it will also throw up on me and say that, hey, there's a data race. It will cause your program to go a lot slower, but if it gives you any output, then it's probably a bad idea. So what this will do is if we go up, it says thread sanitizer right of size 8 at whatever in thread 3. So it tells you exactly what line number had the problem to help you narrow it down. So it's saying that there's a problem here. The only write that happens is to the variable balance. And it's telling me that thread 0 is accessing that memory location at this line. And this is just the stack of that thread. So this is where thread 0 is. And then it's showing me the previous call to write by another thread, in this case thread 2, from transfer happened to be at the same line, so they were both accessing the to account, which is what caused the data race. So gave us all this lump of information. Yeah?
So just curious, so here it keeps referring to thread by like T0, T1, T2. How do we associate that with the actual threads we created? Like, is there an easy way so that we know which actual thread?
Yeah, so the question is, how do we associate them with names of actual threads? So I believe there's a call where you can actually name your thread if you want. In this case, all my threads are doing the same thing, so the name doesn't really help me that much anyways. But yeah, if you had threads doing different things, you can name them. I think they might show up here. I haven't had to do that, though. All right, and just to verify that it indeed does work, so we can go back. Where were we? So we can undo everything all the bad things we did. So this was our fixed code that had no data races and no deadlocks. So if we compile it now with thread sanitizer and run it, we'll see that, hey, it's not throwing up on me. That's probably a good sign. So with all these tools, if they give you an error, there's definitely an error. If they do not give you an error, it does not mean there is a bug in your program, because it only detects it when your program is running. But you can at least have more confidence that you are correct. So if it shows you an error, there's definitely an error. If it doesn't show you an error, doesn't mean you are 100% safe, but you at least have some confidence. So we run it. It takes a lot longer because it's doing a lot of checking, but it did tell us that we didn't have any it didn't detect any data races on that program run or deadlocks, so we can be more confident. And I have the server set up that it actually runs this for you. So part of it is in Lab 5. You're parallelizing a hash table, yay, as one of the tasks. So it will run thread sanitizer on the server to make sure you also do not have any data races or do not have any deadlocks. So any questions about anything about our sweet bank? 8 times faster as long as we have more accounts. But took us a while to get there, right? So we started naively doing it. We had 2 options. We could go slower than a single thread and be safe, or go a lot faster than a single thread and be wrong. So neither initial solution were great. And it took us a bit of doing from everything we've learned in this course to actually make this work and make it run approximately 8 times faster. So this is what you have to look forward to. This is generally what programming will look like from now on. You will have to argue about threads, argue about data races, argue about deadlocks. Otherwise, you're using a single thread, and you're leaving a lot of performance on the table. So you probably shouldn't use things like JavaScript or Python or any of that for anything where performance actually matters. So with that, I'll stick around for a few more minutes in case there's any other question, but that was a successful bank. So just remember, both of you, we're all in this together, and this is